Hello everyone, this is Weimao. This video I will introduce a more complex example using all ArcNLET-Py modules. If you have any problems, please contact us, and our emails are here. This is Mike and this is Dr. Ye. Okay, in this presentation, there are two parts. The first part is a brief introduction, and the second part is a complex Lakeshore example. Okay, let's begin with the first part. When we finish the development of ArcNLET-Py in January 2024, we used the Lakeshore example to demonstrate the use of our new software. But that example is too simple and uses only part of the functionality of our software. That's why we have today's video. We are going to present a more complex Lakeshore example using all the modules in ArcNLET-Py. Specifically, we will model the reactive transport of ammonium and nitrate introduced by septic tanks in Lakeshore area in both vadose zone and groundwater. This is a complex example for advanced users, and here are some resources about ArcNLET. I recommend learning these firstly. And I'm not going to talk about how to download and use ArcNLET-Py. They were covered in the last video, and I will assume that you have watched our previous video and already know how to use ArcNLET-Py. Okay, let's begin the complex Lakeshore example. This is the Lakeshore neighborhood. The Lakeshore neighborhood is located in Jacksonville, Florida, and the study area has a total of 265 septic tanks, as shown in this slide. When we start modeling a new area, we need to prepare some data ourselves. We need to prepare 4 files. The first file is a study area. This should be a zip file with only one polygon to represent the study area. The second file is DEM of the study area. You can download DEM from many websites, such as USGS. Then you should know the location of septic tanks. This file is a multi-point zip file. And the last file is water bodies. This file represents water bodies in the study area. Each water body is a polygon. For our Lakeshore example, you can find the input data at this link. And note that all input files need to use the same projected coordinate. This is really important. And let me open my ArcGIS Pro. Okay, you can find this is the septic tanks in the study area, and this is the water body. We have only one water body here, and this is the DEM, and this is the study area I drew. Okay, let's go back to our PowerPoint. There are 6 modules in ArcNLET-Py, and the first one is a pre-processing module. This module is used to extract data from online Sorghum database, and then the groundwater flow module is used to simulate groundwater velocity and velocity direction based on DEM and soil data. Then the particle tracking module is used to simulate water particle movement from sources to water bodies, and the sources means septic tanks here. Then the VirMod module is used to model nitrate and ammonium reactive transport in vadose zone from drain field to groundwater, and the transport module is used to model nitrate and ammonium reactive transport in groundwater. The last module is the load estimation module, and it is used to estimate mass loading to surface water bodies. Okay, let's begin to run our example with input data. The first module is a pre-processing module, and the input is study area. The outputs are hydraulic conductivity, porosity, and the soil types of the study area. The soil types will be used in VModel module. And I referenced the SoilDB package when developing this module. This is my ArcGIS Pro, and this is the pre-processing module. The first input is the study area, and I can show the study area here. This is what I draw. And then we show the projected coordinate system here. We will use this one in this example. Remember that we said all input files should have the same projected coordinate, but for study area, you can use any coordinates. Why? For example, here I'm using a study area I drew myself. I just created a new polygon, and I could just as well not care about its coordinate system when I draw this polygon. After that, when I want to use this file, I just enter the coordinate system I want here. I think it's really simple. Then, the top depths and the bottom depths are the depths at which we want to extract the soil parameter from the online soil database. Let's suppose our drain field is 50 cm below ground surface, and the water table depth is at 200 cm. So I enter 50 here and use 200 in bottom depth. Then there are 5 extraction measures. We can find the harmonic mean and the weighted average here. I will explain the difference between them. Okay, we can use this slice. If we have 3 soil layers and the water passes through all 3 layers in turn, hydrogeologists will suggest you to use the harmonic mean to represent the average hydraulic conductivity of the 3 soil layers. This is based on the equation of soil water movement. The harmonic mean is usually smaller than the weighted average and is strongly influenced by the minimum value. This means the layer which is most difficult for water to pass plays the biggest role. Okay, let's go back to our ArcGIS Pro. Okay, I will create a new folder here. Output. And give a name to a hydraulic conductivity and porosity output. Porosity. And for soil types, the output file. Soil type. And then just click Run. You can click this View Detail button, and this is information when the module is running. And it's really quickly we can see the outputs here. Okay, this is the soil type. We can close the water body. Okay, this is the output. We can find there are 3 soil types here, and this is the porosity, and this is the hydraulic conductivity. Okay, then we go to the groundwater flow module, and there are 4 inputs. We can use a slice here. There are 4 inputs, including DEM, water body, hydraulic conductivity, and porosity. We have prepared DEM and water body before, and the hydraulic conductivity and porosity have been created using the pre-processing tool. We can directly select them here. Okay. This is the groundwater flow module, and we can choose DEM, Lakeshore, and water body, hydraulic conductivity, and porosity here. Okay, and these are the parameters. I will change the smoothing factor to 50. Then I will enter the name of the output. This is the output folder. I will name the velocity as velocity 50 and the velocity direction in the same folder as velocity direction 50. The smooth DEM will be used in VirModel module, and we will enter the name as smooth DEM 50 here. And this is the gradient. We can name as gradient 50 here. Okay, and I will click the run button. The module will run. And we can click here to view the details. Okay, this is the output. We can find this is a velocity direction, smooth DEM, and gradient. Let's go back to the PowerPoint, and I will explain how the groundwater flow module works. Okay, we can see this slice. The blue line represents the groundwater table, and the yellow line represents the land surface. When we smoothing the ground surface after 50 times, we can get a plane similar to groundwater table, and the 50 times is the smoothing factor. Then the question is, how do we determine the smoothing factor? Okay, let's see this slice. Suppose we have 4 monitoring wells here, and on the right, there is a scatter plot with measured groundwater table on the x-axis and the smooth land surface on the y-axis. Therefore, we can plot these 4 wells, which are these 4 yellow dots. Then we can fit this data with a line, like this red line here. This line has a slope A and an intercept B. When the slope is close to 1, we can assume that the smooth DEM surface is very close to the surface of water table. The intercept, it means the distance from the smooth DEM to groundwater table, like here. So in the groundwater flow module, all we need to do is to keep adjusting the smoothing factor to ensure the slope A is as close as possible to 1. That's why I named the output of groundwater flow module with smoothing factor here. I can use many smoothing factors like 40, 50, and 60. Then I can calculate the slope and choose the best one for further calculation. Then we will go to the second module, the particle tracking module. And this module is used to simulate water particle movement from septic tanks to water bodies. And this module requires 5 input files, including source location, water body velocity and velocity direction, and porosity. Okay, I can show the input here. This is water body and velocity. This is velocity direction, and this is porosity. I will enter a name here, and in the output folder, I can enter as passes 50. Okay, then we can click run here. It's really quickly, and we can see each line represents the transport path of a particle from a septic tank to a surface water body. Then the WIRMOD module is used to simulate nitrate and ammonium reactive transport in vadose zone from drain field to groundwater, and we show multiple OSTDs here. Then you can find there will be 3 checkboxes because we have more than 200 septic tanks, and each septic tank is located in a different location with different parameters such as hydraulic conductivity and porosity. Therefore, we need to use different parameters for different septic tanks, and we show these checkboxes, and these files are used to input spatial parameters. And let me expand the hydraulic parameter here. We can find these are hydraulic parameters associated with soil types clay, and if we choose multiple soil types here, we can find these parameters disappear. This is because we will use the default values for each soil type for the calculation. Okay, I will choose all of them, and let's use this is the septic tanks, and this is the hydraulic conductivity, soil porosity, DEM, and smooth DEM, and soil types. Okay. These are the concentration of ammonium and nitrate in the drain field, and this is the distance. This distance is an important parameter, and we can use this slide to explain. The parameter distance means the distance between drain field to groundwater table, and the distance equals A minus B. Remember, in groundwater flow module, we get the distance between land surface and the groundwater table. Here, let's intercept in this figure the distance between land surface and the groundwater table. That's A, and B is 1.5 feet typically. Therefore, we can calculate distance and enter it. I will use 100 here. Then we need to enter a folder here. The folder output, and I will create a new folder named WIRMOD, and click this and show this folder here. Then we can click run. Oh, it's finished. And we can find the folder output here vir mode, and this is result. This is septic tanks, and we can click and open its attribute table, and then we can find two columns at end, which are the concentration of nitrate and ammonia. This is a concentration of nitrate and ammonia coming out of the drain field, passing through the vadose zone and into the groundwater. We can see this figure. It means the concentration here. And in the output folder, we can find another file. It's this file stores the change of nitrate and ammonia concentration from the drain field to groundwater per file for each septic tanks. Based on this data, you can plot a figure like this. Okay, let's go to the transport module. The transport module is used to calculate nitrate and ammonium reactive transport in groundwater from the point beneath drain field in groundwater to surface water body. This one. There are three inputs. The first one is the septic tanks, and we use the results calculated by Virmod here because we need raise concentration. And this is a water body, this is particle passage, and because we want to calculate both nitrate and ammonium, we should checkbox here. And let me enter name. The output folder, I will name as demo nitrate and demo ammonia. Okay, the specific Z mode were used here, and for other parameters, we will use the default values. Then we can run the module, but because the software can't run very quickly currently, it will cost almost 10 minutes. Instead of waiting, I will just show the output I prepared before. Here. Okay, there will be 4 outputs, 2 for nitrate and 2 for ammonium. And for nitrate, there will be a plume, and there will be a raster and a shape file. The raster is for plume, and the shape file is calculation information stored during our model run. Okay, this is the nitrate plume, and this is the ammonium plume. Like this, and this is for nitrate. This is the last module, load estimation module. Let me drag a file here. The nitrate information and the ammonium information. Load estimation model will generate a name here. If you don't like it, you can change it yourself, and you will just we will just press run button and click view detail and parameter. These are the results. And this file is for nitrate, and this file is for ammonium. We can open one file. The first line -1 means groundwater, and the second line 30 means the surface water, and we can find the surface water, and we can click this. We can find each feed ID is 30. Then we can find the mass output load, multiple risk, and mass input load, and mass removal rate. Thus, we can obtain the mass of nitrate and ammonium entering surface water bodies. Let's our results. Okay, this is a complex Lakeshore example. If you have some problem, please contact us. Thank you very much.